Hi everyone. So we are going to discuss about kinetic theory of gases and molecular interpretation of temperature before we proceed to the laws of thermodynamics. Okay, now I want you to recall in your chemistry, what is Robert Boyle's law? What does it tell us about the behavior of gases? Now, why do we have these laws with regard to expansion of gases? It is because we cannot use the thermal expansion that we use for solids and liquid because there would be greater expansion for gases. So we will have to use different equations for gas. And also, let's define some terms like equation of state. When we have the equation telling us the relationship between volume, temperature, and pressure, that is what we call equation of state. And then we have to analyze gases wherein the pressure will be equal all throughout the container. For example, you have a gas confined inside a container. We have to wait for the pressure or the temperature to be the same all throughout before we can describe the gas using the equation of state. So I will show you now an animation about gas laws, so wherein volume can be held constant, pressure, and also temperatures. Let's watch this animation. Okay, so let's take a look at this animation wherein we have here the pressure reading, the temperature reading, and then we can also add heat to the system. So let's say for Boyle's law, let's say that temperature is constant. Okay, what do you think will happen to the pressure as the volume is increased? And what will happen to the pressure as the volume is decreased? Let's take a look at this. So if temperature is constant, and then we try to decrease the volume, so you can see here that the pressure has increased. And then if we try to decrease it more, again the pressure is increased. But if we try to increase the volume, the pressure has decreased, held constant. Okay, what will happen is the temperature is still held constant and then you increase the pressure. So we are expecting that it will expand. Okay? So this can move. Okay, this container can expand when the temperature is held constant. So let's try to take a look at Boyle's law. So you can see here that it was discovered by Robert Boyle, wherein the volume is inversely proportional to the pressure if the temperature is held constant. So that means as the volume increases, the pressure decreases. And as the volume increases, the pressure decreases. But as the volume decreases, the pressure increases. And PV is equal to constant. So you can see here the experimental data wherein P times V will be constant. That's why if there should be change in pressure, there should be change in the volume so that this product will still be constant. So that is Boyle's law. Next, okay, Charles' law tells us that volume is directly proportional to temperature. As we increase the volume, the temperature also increases if the pressure is held constant. Or as the temperature is increased, the volume also increased if the temperature is or if the pressure is held constant. So that is according to Charles or Jacques Charles. So there is a direct proportionality between temperature and volume. Now this graph was drawn and then it was extended. So you can see here At zero volume, you will have a temperature which is negative 273. So that is around negative 273.15 degrees Celsius. So that means at negative 273.15 degrees Celsius, which is equivalent to Kelvin or 0 Kelvin, so that means that there's no volume anymore. That's why we have considered Kelvin as the absolute temperature or the absolute zero. Okay, now I want you to take a look at this one. What if we increase the temperature? What will happen to the pressure if the volume is constant? So let's try to increase the temperature. Then I want you to observe what happens to the pressure. Okay, so as you can see, the pressure is increasing if the temperature also increases. But if we try to pull this down, what will happen to the pressure? The pressure reading decreases as you cool this down or as the temperature decreases. So they are also directly proportional to each other provided that the volume is held constant. So that is another relationship. The gas law portrayed by that animation would be the Gay-Lussac's law. Now this is the system. You have the temperature, then a water bath, then you can add heat to the system, and then there will be a pressure reading. So this was the relationship, or this was the graph where it's telling us that the temperature is directly proportional to the pressure. As the temperature increases, pressure also increases. So that is Gay-Lussac's law. Take note also that ideal gas has certain limitation wherein we cannot use this one or if the gas is near the liquefaction point or its boiling point or that the gas will now be liquefied. And also it doesn't apply if it has very high pressure and it has very high density. That's why the term we have the ideal gas law because real gases cannot be confined with this law. Okay, we will also try to solve sample problems on gas laws. One are the basic postulates of kinetic theory. We have there are a large number of molecules n, each of mass m, moving in random motions with a variety of speeds. Take note that gases, they are not confined in one direction, but they will be moving in different directions. The molecules are on the average far apart from one another. That is, their average separation is much greater than the diameter of each molecule. So that tells us about the distance of the molecules from one another. The molecules also are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Okay, although molecules exert weak attractive forces on each other between collisions, the potential energy associated with that attractive force or with that particular distance is very small compared to the kinetic energy. That's why we neglect that potential energy or that weak attractive force. And then also collisions with another molecule or the wall of the vessel are assumed to be perfectly elastic. So it will not be attached to the vessel. So the vessel will not be deformed during collision. So there is an elastic collision like the collisions of perfectly elastic billiard balls. So we have here now
the description of the kinetic energy of molecules. Kinetic energy of molecules equals 1/2 mv squared and is also equivalent to 3/2 kT. And
And
further
further
derivation
derivation
of
of
the root
the root
mean
mean
square of the
square of the
velocity, we
velocity,
have
we have
square root of
square root of
3 kT
3
over
over
m.
m, moving faster and faster, which will result to the expansion of the material. So we have here a graph of the James Clerk-Maxwell distribution of speeds. So we have here the average speed, the root mean square, and then the most probable speed of the molecules. Okay, and then you can see here also a graph relating temperature and the speed. So as you can see that there is a shift to the right. As you increase the temperature, the molecular speeds also increases. So here is the summary of James Clerk Maxwell discovery. As the root mean square of the velocity increases with temperature, the whole distribution shifts to the right at higher temperatures. So you can see here in the graph that there is a shift to the right. The minimum energy required for a chemical reaction to occur also is known as the activation energy. Okay, again, the number of molecules that have kinetic energies in excess of the activation energy can increase greatly for a small increase in temperature. So let's take a look at this graph. So you can see here in the graph, we have here the fraction of molecules greater than the activation energy. So we have the activation energy here. And based on Maxwell's distribution of speeds, at high temperature, there's a shift to the right. So looking at this part, you can see here that there is also an increase in the number of molecules. And the number of molecules with that activation energy can increase also the activation or the chemical reaction. So now, that is the reason why, as you increase the temperature, as you increase the temperature, the chemical reaction also occurs at a faster rate, okay? So that's the reason behind it. Now let's take a look at diffusion. So let's try to look at this animation about diffusion. Okay, so let's see what is diffusion. So let's take a look at the particle rate flow, the scale, and then let's have the number of particles. Okay, so you can see here that this is more concentrated. This has no particle. So what will happen if we remove the divider? So the particles will move towards the area with lower concentration until it reaches equilibrium. So that is about diffusion. So maybe later I can show you a demonstration on diffusion. So you can see here the diffusion takes place because of random movement of molecules. So in the animation, you were able to see the particles are moving at different directions. And then diffusion also depends on the concentration or the number of molecules or moles per unit volume. Molecules are in random motion, but there is still a net flow of molecules. You can see in the animation that the net flow would be to the right, as you can see it from in your screen, so it's to the right. Then, until the concentration becomes equal. Okay, the diffusion will stop if the concentration becomes equal. The greater is the difference in the concentration, the greater will be the flow rate of the diffusion until it reaches equilibrium, okay, or until the concentrations are equal. So let's now solve problems on gas laws. Okay, so I'll show you the derivation of the formula for the kinetic energy, the 3/2 kT. So you have here, for example, a box. Or for example, the gases are confined inside a box, inside a square box. So assuming that pantay-pantay yan. So you have here the area. We can consider this one as the area. And then let's have here the length. That the particles are moving inside in different directions. So what can you say about the momentum of the particle? So for example, the particle is moving to the left, and then of course it will bounce back. So it will have again a momentum to the right. So let's say the initial momentum, recall that momentum in your mechanics is mv. So we have the initial momentum is m, v1. Let's consider first the x component. So vx, vx, it will be negative because it's towards left. And then you have, this is the initial, and then you have the final, it will be m vx to the right. That's the final. So here, the total change in momentum would be final minus initial. So that will be m vx prime minus the initial is negative mvx. However, take note that vx there will be the same. The difference is only the direction. So we can express now the change in momentum, or delta mv or delta p, as equivalent to 2 mv along x. So you have to take note of that. And then we are going to analyze the force exerted. Recall also that there's a relationship between force and momentum, wherein force is equal to the change in momentum per unit time. And for this situation, what we are going to consider, the delta t, would be the back and forth movement of the particle. That's the total time. So it has to travel 2L at a particular delta t. So we have the velocity would be 2L. So it has to travel 2L divided by the total time interval. So we now have here the delta t can be expressed as 2L divided by Vx. So let's recall this one. Again, as I have mentioned, force is a change in momentum per change in time. So this is our change in momentum. So we can now have an equation: force 2mvx divided by our delta t could be expressed as 2L over Vx. So this will become, cancel na yung 2. We can cancel out 2, and then we can square this one. So we now have m Vx squared divided by L. That will be the force exerted by the particle. So we have m over L Vx squared. But take note that in reality, they can have different directions. So it's not just along x component. And we also consider the number of particles. So that equation could actually be expressed as F equals m over L, but the velocity would be the different velocities of the different particles. So we now have Vx squared 1 plus Vx 2 squared plus Vx particle 3 squared up to n Vn along x squared. Okay, so we have that expression. Now take note also that we can express this as an average. If we have an average velocity along x squared, that will be this. The expression Vx1 squared, we add all these velocities, x2 squared plus Vx3 squared up to n. Then we divide it to the number of particles. So we can express it as n then their average squared. So let's substitute this equation. Let's substitute that equation to this. Okay. So we now have the new equation: force is equivalent to m over L, then n Vx squared, yung average. Okay? So in mechanics also, let's recall that we have different components. If we are going to get the resultant, we have Vx, the component Vx squared, plus Vy squared, plus Vz squared, and so on. And take note also that we can have, or we can consider them as having same velocities in different directions. So we can further express this, if they will be equal, Vx, Vy, Vc, this expression, I will use a different color. Okay, this expression now, if they are equal, we can now express this as v squared. 3, I will be using Vx squared. Okay, so we can express it this way. Therefore, our equation here, Vx, we can change it to, we can divide everything by 3. So we now have force is equal to m over L, n, then you have here v squared. That's already the resultant divided by 3. Okay, so the force now is m over L times n, then v squared divided by 3. Next, let us recall that pressure is force divided by area. So the force that we were able to derive, we will use that. So that is, that's equivalent to m over L Okay, the force now is equivalent to this, m over L and v squared. Okay, force is m over L and v squared divided by 3. So let's check divided by area. So the pressure is divided by area. Let's rearrange this one. We can now have 1/3 m n velocity squared average divided by a L. Okay. So take note that AL, if we are going to analyze the box again, we have the box, then we have the area and the length. This is our area, and then we have here, it can now be expressed into volume. So our pressure now is equivalent to 1/3 M N V average squared divided by the volume. So we can now, you can see that there's already an expression for PV. PV is equivalent to 1/3 M N V average squared. And take note that in the previous, maybe in your chemistry or in your chemistry subject, you were able to get a relationship of PV is equivalent to NKT. This is also related to PV equals nRT. So let's just equate these two equations. Let's just equate them. So we now have 1/3 M and V average squared is equivalent to NKT. So we can now cancel out N. And you can see here that we have an expression for mv squared, which is could be related to kinetic energy. Kinetic energy is 1/2 mv squared, so we can multiply both sides of the equation by 1/2. So we now have here 1/3 1/2 mv squared is equal to 1/2 kT. So you can now see that this could be expressed as kinetic energy. So let's derive it further. Let's just place it here. 1/3 Ke is equivalent to 1/2 kT. So, and the final answer would be Ke equals 3/2 kT. Okay, so that is the derivation of the kinetic energy and how it's related with temperature. Okay, so let us solve sample problems on gas laws. Number 1, determine the volume of 1 mole of any gas at STP, wherein STP is the standard temperature pressure. The standard temperature is 273 Kelvin, and then the standard pressure is 1 atmosphere, assuming it behaves like an ideal gas. So take note of our equation for ideal gas. Okay, our equation for ideal gas, we have PV equals nRT. What we wanted to look for is the volume. So the formula for the volume is just nRT over the pressure. So we just have to substitute the given N, which is 1 mole, and then R, the constant is 8.315 joule per kilogram or joule per mole Kelvin. So 8.315 joule per mole Kelvin times the standard temperature, which is 273, divided by the pressure, which is 1 atmosphere, or we have to convert it to Newton per meter squared. Take note that is equivalent to 1.013 times 10 to the 5 Newton meter or Newton per meter squared. So we have here 1 times 8.315 times 273 divided by 1.013 times 10 to the 5th. So the answer is 22.4 times 10 to the negative 3 meter cube. Okay, so here's our answer. The volume is 22.4 times 10 to the negative 3 meter cube. Now to show us the cancellation of unit, we have here mole. Then our constant is in joule per mole Kelvin. And then you have the temperature is in Kelvin. And then for the pressure, we have Newton per meter squared. So let's see. We can cancel out mole. We can cancel out Kelvin. And then joule also is expressed as Newton meter. Therefore, we can cancel out Newton. And then we will add since it's Newton meter per meter cube or per meter square, so that will result to meter cube. Okay, so our answer is 22.4 times 10 to the negative 3 meter cube. Let's have the next one. A helium party balloon, assumed to be a perfect sphere, has a radius of 18.0 centimeter. At room temperature 20 degrees Celsius, its internal pressure is 1.05 atmosphere. Find the number of moles of helium in the balloon and the mass of helium needed to inflate the balloon to these values. So we have to look for the number of moles. But for us to be able to do that, we can use the ideal gas law. So you have here PV equals nRT. Now what we wanted to do is to look for the number of moles we are going to look for N. But we have to look for the volume first. Since it's a sphere, so we can solve for the volume. 4 pi or 4/3 pi r cubed. We can solve for the volume of a sphere as 4/3 pi r cubed. So let's have the volume. 4 divided by 3 times pi times the radius. Since the radius is in centimeter, we can convert it to meter, so that's 0.18. And you will have a volume of, our volume is now equal to 0.0244 meter cube. Since we already have a volume, we have the pressure, we have the constant, we have the temperature, so we can now solve for N. Okay, N now is equivalent to PV over RT. Our pressure is 1.05 atmosphere, and then the volume is 0. The pressure is 1.05 atmosphere, but we have to convert that in Newton per meter squared. So let's convert 1.05. 1 atmosphere is equivalent to, as I have mentioned earlier, 1 atmosphere is equivalent to 1.03 or 0.13 times 10 to the 5 Newton per meter squared. So using that, let's just multiply so that we can get the pressure in Newton per meter squared. So we have 1.05 times 1.013 exponent 5 or exponent 5. That will give us, here we now have an equivalent of 1.064 times 10 to the 5 Newton per meter squared. So let's substitute this one to this. It's 1.064 times 10 to the 5 times the volume given, or the volume that we have solved earlier, is 0.0244 meters squared, divided by our constant is 8.315 joule per mole Kelvin. And then the temperature, since the temperature is 20, so you just add 273, that will give us 293 Kelvin. So solving for this one, it will give us the number of moles. 1.064 exponent 5 times 0.0244 divided by 8.315 times 293. Here, our answer is 1.0656, or it could be rounded off to 1.066. Okay, moles. Okay, so 1.066 moles, so that you can have, or you can inflate the balloon to the volume of 0.0244 meter cube. Okay, so next question. An automobile tire is filled to a gauge pressure of 200 kilopascal at 10 degrees Celsius. After driving 100 kilometers, the temperature within the tire rises to 40 degrees Celsius. What is the pressure within the tire now? So you can see here the relationship of pressure. So we have pressure and then temperature at 10. Then here we have here a general relationship wherein we have P1, we have P1 V1, T2 equals P2 V2 T1. But here, the volume is held constant, so we will just look for the relationship between pressure and temperature. So we have P1 T2 equals P2 T1. And in the problem, we are looking for the second pressure. So our formula is P1 T2 over T1. That will give us the new pressure P2. Okay, our pressure here given is 200 kilopascal. The gauge pressure Okay, the gauge pressure is 200 kilopascal, but there is an atmospheric pressure that we have to add equivalent to 101 kilopascal. So the pressure here should be 200 kilopascal plus the atmospheric pressure of 101 kilopascal. So that is equivalent to 301 kilopascal. Then next is the temperature. The temperature reading here is 10. So add 273. That will give you 283. That is T1. So 283 Kelvin. And then our T2, it's 273 plus 40. So that will give us 313 Kelvin. So let's now substitute. We have P2 equals 301. So that's kilos. So we add 3 zeros times the temperature. The second temperature is 303 Kelvin divided by 283 Kelvin as T1. So our pressure now, 301,000 times 313 divided by 283. Okay, the pressure now should be 333 kilopascal. Okay, so you can observe here that as the temperature is increased, the pressure has also increased. Next item. What is the average translational kinetic energy of molecules in a gas at 37 degrees Celsius. So we have to use the relationship of kinetic energy and absolute temperature. So we have an equation: kinetic energy is equivalent to 3 halves kT. Okay, but take note again, if we are referring to the absolute temperature, so you have to convert the temperature to Kelvin. So we have 37 plus 273. We'll just use 273. So that will give us 310 Kelvin. Okay, so we now have the kinetic energy is 3 halves times 1.38, that's a constant, times 10 to negative 23 joule per Kelvin. Then, of course, multiplied by the absolute temperature, 310. So 3 halves, 3 divided by 2 times 1.38 times 10 to negative 23 times 310. It will give us a kinetic energy of 6.42 times 10 to negative 21 joules. Okay? So that will be our kinetic energy. Alright, so that will be the end of the problem solving in gas laws.